Welcome to Scamp-B. Scamp-B is a simulation of a simple computer that can be controlled through a set of data, address, and control keys. Not only are its 16 general-purpose registers, program counter, and instruction register made visible through lights, but also the contents of the 256 memory words are shown on the memory map screen. Scamp-B has a set of 16 instructions and many system functions for input, output, and control. Programs can be input via the keys or written using the integrated assembler. Also, included with Scamp-B is a simulated paper tape reader, which runs as an independent program.
Well, thank you, Serena, for that very professional introduction, but I'm afraid for the rest of this demonstration you've got me. So before we move on, let me just point out that these mag tape devices are purely graphical and are a hangover from Plasma's project, PlasmaSim. You can spin them with a system function, but they don't do anything other than that. You can light the lights up as well. So here we have normally just the memory map, the register display here, key switches here. So let's try a few of these switches out. First of all, under the program section here, we can clear memory and we can zero the registers. Very useful switch. Let's clear the memory and zero all the registers. The next most interesting switches are these here for loading. These can load the registers, the memory, the instruction register and the program counter. So if we were to set on the data keys a value such as all ones, then we can load those ones into a register. Now the register we load them into is identified by these 4 address keys here. Currently they set all off, so that's 0. So if we do a register load, hey presto, register 0 has all the ones from the data keys set in it. If we were to switch to register 2 and do that again, we'd end up with register 2 all lit up. Conversely, we can clear the data keys down, write to the register again, and it's gone, write to register 0 again, and it's gone. So now that we know we can load the registers, let's put a value in register 0. Now I'm assuming I'm not going to explain hexadecimal, but that represents hexadecimal 4-2. There are some links in the user guide to various tutorials on hexadecimal and binary, etc., which you need to look at if you don't understand. So there we've got 42, as we call it, on the data keys. So we'll put those in register 0, and there you are, hexadecimal 42. Now we can check that that's what it means by clicking this key, which changes from binary to decimal, and there it says hex 42, which is decimal 66. So a useful thing to be able to do. So now we've got 42, hexadecimal 42 in register 0. So let's now put a value in the instruction register, and a value that we put in the instruction register will be executed as an instruction. So here's one I happen to know, which is 4002, coincidentally, and this writes whatever's in register 0 to the upper over here. So if we put that data into the instruction register, there it is, 4002, check that, 4002, and if we look over here at the upper, we see we've got the hexadecimal 42, and that equates to decimal 66, and it also equates to ASCII character capital B. If we want, we can keep pushing this instruction 4002, which is on the data keys, into the instruction register ad infinitum, and every time we do it we see that we get another upper right of the data that's in register 0. So we've shown writing to the instruction register, we've shown writing to the general purpose registers. Now let's try writing to memory. So there's the data still. We'll leave it as it is, 4002, and we'll leave the address at 0, that's the memory address, and we'll write to memory. And there in location 00 we've got 4002. Now that we've written this 4002 to memory, we've in effect got a program. Sat in memory is an instruction. So we should be able to step, using the program key step here, step the program and see what happens. And you'll see that it stepped to the next address. It wrote yet another register 0 to the upper. It obeyed the instruction and it went on to the next location in memory. You'll see that the program counter has gone up to 1. It was sat at 0. If we 0 the registers, it goes back to 0 there. But of course we've also zeroed the data, so if we now write to the upper, or run the program again through the step function, we now write 00, which is what is in register 0. So now we've shown that if we put an instruction into memory, we can use the step key to execute it. So this is the start of programming. So let's clear the memory, and now I'm going to put an instruction in there which actually loads register 0 with a value. So we'll stick with the 42. The instruction is B042. So if we put that in memory location 0, there it is, that's the instruction B042. And then if we go to the next memory location by pressing the increment key there, that sets the next memory location, number 1, and we put our old favourite instruction 4002 in there, then we have two instructions. We now press the 0 key, which takes the program counter back to 0 and sets a little box around the first instruction. We can step through this program, two instructions. So the first one loads 42 x42 to register 0. The next instruction writes the value to the upper. Now we could write several 4002 instructions into memory, so that it would keep writing the value in register 0 to the upper, or we could put in a jump instruction which would say jump back and do that instruction again. Now that instruction is 5001. The 1 says jump to address 1. The 5 is the jump instruction. So if we put that in the next location, so we increment that memory address and we write it to memory, there we have the 5001 in there. So now if we step through the program, first going to the start with the 0 key, this is what happens. When it gets to there, to 5001, it jumps back to address 1. So each step makes it write the data to the upper each time. And we could run the program now by pressing the run key. And as you can see, it's just oscillating between those two instructions. So that's a running program. Now we can make this a little more interesting if we change the instruction at memory address 2 to be a decrement and jump on 0. And that's a 7001. That'll decrement the value in register 0 and jump if it's not 0. So let's put that into memory at address 2. So there you can see, and it's interpreted it there at the bottom. Subtract 1 from register 0, if not 0, jump to address 1. So now if we go back to the beginning of the program with the 0 key and step, we see that in register 0 we've got the 42 as before. We've written it to the upper, and now it's decremented it, and it's 41. And now when we write that to the upper, it goes from 42 to 41, decimal 66 to 65, and letter B to A. So if we run this program, it goes all the way down to 1 and decimal 1, and there isn't an ASCII value relating to that. And you can see if we look at the upper here, it's done 133 instructions with 65 jumps, that particular program. So this program runs perfectly well, but it may be that we wanted to stop it at a particular point to find out why it had done a particular thing. And we can do this with the break mechanism. These data keys also called data break. So we could say that as it counts down from 42, hexadecimal 42, down to 0, we could say, well, what happens when it gets to 26, hexadecimal 26? So we set that on the data break keys, 0, ready to start again, and we set this break key here. Now that lights up the value on the data keys, what we're looking to stop on. The register we're going to stop on is set on the select register keys here, and it's 0, which is what we want. So we'll run the program, and you can see it counting down. As soon as it gets to hexadecimal 26, it stops and a little blue light comes on register 0. So as well as the blue light, we've got this remark here, stopped on break. If we look at the instruction register, it's got the 4002, which is the upper right instruction, ready to be obeyed, but has not been obeyed yet. So if we tick or step, then we see that it moves on, and the 26 is written to the upper, which is an ampersand character. Now if this were a real machine, we wouldn't be able to see the memory. That would be invisible. But on this simulation we can. So we got another kind of stop, and that's to stop on a memory location. So I could click on that memory location there, 4002, and it changes colour. And that means that we've now set a break on memory. So if I run the program, start it again, and run it, as soon as it gets to that first 4002, it stops. And we can keep running it, and it'll stop every time round the loop. And if we like, we can set 2 breaks, so it'll stop on that as well. And we can unset the breaks by just clicking again on the memory locations. So now we've pretty much looked at all the things we can do by entering data through the keys, putting them into memory, and running through the program step and run mechanism. However, in a real machine, you'd want to be able to input little programs or even large programs by some other mechanism. You don't want to have to use the hand keys every time. So traditionally one would use a paper tape reader. So what we're going to do now is to load up our paper tape reader and try loading a program via that. So here we can see the paper tape reader running alongside Scamp-B. So here's the paper tape reader with a representation of a blank paper tape loaded on it. We can now take advantage of the fact that we're running on a host computer, and we can use its file system to load a paper tape representation. I prepared a file earlier called example.pl8, and if I open that, it writes it onto the paper tape. There are the holes, and it's got its name on there as well in red. So if we zoom in and have a look at this this tape that we've loaded, called example, we can see there are 8 lines of holes. Now it takes 2 lines of holes to create a memory word, so there's going to be 4 instructions there. So the tape's loaded on the paper tape reader, but to load it into Scamp-B we need to set the paper tape reader to run. So click the run key, and to load the tape into Scamp-B we use this load program key and we click it upwards for PTR. And there it is, it's loaded into memory. But before I run this program I'm going to show you how I created it using the assembler. So if we click on File here and Open, then we can see our example file here, so we'll double click on that and there it opens it up. And that is written in mnemonics, which are all listed in the TOSB instruction set. This aids programming. It's much easier to write in assembly. You can put in comments and it's very easy to modify. So how I created the tape file was to click on the tape here and click PTR8, and then I assembled the program. It says down here that it seems okay. From this point you can actually click load, which will load the program straight into memory. And there it is. If however I wanted to edit it again, I could just de-iconize the window that just got iconized and carry on changing it. But I'm not going to talk about the assembler today. I'm just going to show you this file running. So to run the program we'll click Run. And what it's doing is writing the value of each address to itself all the way up memory, starting at the top and going backwards. Now what it's going to do in it is overwrite itself, because it's actually got to write location 3, which actually contained a little bit of the program, so it's overwritten it and it said illegal instruction and stopped. But what this program probably demonstrated better than anything is that Scamp-B is a pretty slow computer. In real life that should have flashed before your eyes and written everything to memory. But it's a nice human pace that enables the would-be programmer to see what's going on. So to round off this demonstration today I'm going to load another program via paper tape, so it's authentic, and show a little bit more what Scamp-B can do. So we'll press load, we'll choose this two Morse monkeys, as it's called, click run and load, and there's the tape now being loaded in. This program picks random letters at random from the alphabet and prints them out in Morse code, so it's all a bit of fun. So if we run the program we can see what it does, and thanks for watching.
Thank you for watching this demonstration of Scamp-B.